Okay, this is section 7.2. So in 7.2, we're simplifying radical expressions. And something that we have to just realize back from Algebra 1 is just simplifying them in general, like up here, the square root of 12. So if we have the square root of 12, we know that it's a square root, so what we're dealing with is perfect squares. We want to rewrite 12 as the product of a perfect square that goes into 12 and then whatever else multiplies to be that. So the perfect squares, remember, are any integer squared. So 1 is a perfect square, 4 is a perfect square, 9 is a perfect square, and I'm getting these numbers because like 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and so on. 12 has one perfect square factor, 4, and we would have to multiply 4 by 3 to equal 12. We do this so that we can basically take the square root of 4 out, which is 2, but we're still left with the square root of 3 left over because it's not totally a perfect square, but it does have a factor that is a perfect square. When we have square roots, doesn't have to be square roots, but in this case, the square root of like x to the third power. In Algebra 1, we learned to regroup x to the third, or whatever it is, into as many groups of 2's if it's square roots as possible, because those can be square rooted. The square root of x squared really just equals x, so it comes outside of the symbol, and then we would have the square root of x right here left over on the inside, so my final answer would be x times the square root of x. Now that was Algebra 1 where we were dealing with simplifying square roots, and that's something that you already learned, but in Algebra 2 we're going to be simplifying cube roots, fourth roots, and so on. So what we're doing in example 1 is simplifying the radical expressions. It says assume all variables are positive, but what I need to be more specific in the directions is that I want all answers in radical form, meaning we want our answers to have a symbol in it, not in exponential form. Sometimes the questions start out in exponential form, sometimes they start out in radical form, but I want all of the final answers in radical form for this section. So, if I said, what is the cube root of 125y to the 6th? There are a couple different ways that we can do this. One way is take this out of radical form, put it in exponential form, and simplify it that way, if it's helpful. So what I would do is take the entire base, which is 125 y to the 6th power. And because it's being cube rooted, this is like taking it to the power of 1/3. I would then use the power rule, and I would get 125 to the 1/3 times y to the, multiply these, 6 times 1/3 is really 2. 125 to the 1/3 can be totally done in the calculator, but it also can be done, if we memorize it quickly, knowing that 125 is a perfect cube. 5 times 5 times 5 is 125. But 125 to the 1/3, same thing as the cube root of 125. It just equals 5, and then we would have y squared. Now, here's the issue with this. It wants us to have all final answers in radical form, but this one actually didn't even need a radical. Radicals are when you would have a final answer that has an exponent that's a fraction. So this one, no radical is even in the actual answer. So that would just be the final answer for that. Now, if you didn't want to do it that way, a second way to do this would be basically rewrite all the numbers inside as perfect cubes. So 125 is a perfect cube in of itself, and I could regroup y to the 6th as y to the 3rd times y to the 3rd. And then I could take the cube root of each separate part. The cube root of 125 is 5. The cube root of y to the 3rd is y, and the cube root of that second y to the 3rd is also y. 5 times y is also 5y squared. So you can think of it that way as well. Your choice. I've kind of flipped back between one method and the other depending on the question. Next one, we have here 625 j to the 8th, k to the 4th, all raised to the 1/4 power. I'm just going to use the power rule and use the first method. So this is going to be 625 to the power of 1/4 j to the power of 8 times 1/4 is 2. And then k to the 4 times 1/4 is 1. So 625 to the 1/4, I wouldn't know it because I don't have any of my like fourth powers memorized really, but 625 to the 1/4 just perfectly equals 5. And then we have j squared times k. This one also does not have a radical in the final answer. Part C, we will have some radicals in our final answer. So we have a problem that's set up in fraction form. I see like numbers, coefficients. I see variables with negative exponents, with fraction exponents, all sorts of different things that we've learned so far. First thing is, let's simplify the coefficients. 15 divided by 5, that's just 3. Now for the d to the second over d to the first, I'm going to use the quotient rule. 2 minus 1 is 1, so this is going to be 3d. And then we've got e to the 2/3, which there is nothing to combine with that. And then using the quotient rule for the f to the first divided by f to the -4th, you would do 1 minus -4. 1 minus -4 is 1 plus 4, which is 5. So this is the answer that we would get. Now they want all answers in radical form, meaning if you do get any part in your expression that has a fraction exponent, you should rewrite that in radical form. Now the 3d f to the 5th, nothing I would need for radicals there, but e to the 2/3, you would need to rewrite this as the cube root, because the denominator of the exponent fraction is always the root, the index. The radicand, the number on the inside, is always the base. And then the numerator is always like the little exponent that goes next to the number inside the radical. So this would be 3d f to the 5th times the cube root of e squared. Okay, next one. So we've got here the cube root of x over y to the 7th. Now there are a couple ways we can go about this problem, but the first thing I want to do here is cube root the numerator and the denominator. That's the first part. That's the first property that we can take. The cube root of an entire fraction is the same thing as the cube root of the numerator divided by the cube root of the denominator. Now the cube root of x can't be simplified or anything like that, but the cube root of y to the 7th can be simplified. Something that's super important about simplifying radicals is that this exponent inside should never be greater than the actual root. If it is, it means it can be simplified. So what we do to simplify this is we regroup the y to the 7ths as many y to the 3rds as we possibly can. We break it up basically into y to the 3rd, y to the 3rd, that would be y to the 6th, and then we have an extra y here. Now each cube root of y to the 3rd will cancel out to just be y. So this will end up being, in the numerator, we don't change anything up, but this is going to end up being the cube root of one of those y to the 3rd powers. This is going to be y on the outside. Another cube root of y cubed is another y on the outside, and we're still left with a cube root of a single y. Basically, both of these things end up cube rooting completely outside of the radical, and then I'm going to finish my work all the way over here. We would get the cube root of x over y squared times the cube root of y. Now for another fun rule in math, we're not allowed to have any radicals in the denominator. So just like we can't have negative exponents with radicals, we can't have radicals in the denominator. It's a thing. So what we have to do is get rid of this in the denominator. How we do that? It's called rationalizing the denominator, and what we would need to do is multiply the numerator and the denominator both by whatever the cube root of whatever will cancel out with the cube root of y. So what's confusing is it's not going to always be like, you know, just like the cube root of y, which sometimes that happens. You have to really think about it. If we have the cube root of y to the 1st power, we need to basically make this y to the 3rd power. So we'd have to multiply by the cube root of y squared. Why would we do that? because y to the first power times y to the second power is y to the third power. What happens here in the denominator, which I'll start with the denominator, we have y to the second, and then when we merge these two things together, this ends up being the cube root of y to the third power, which is exactly what we need because the cube root of y to the third power really will cancel each other out and just equal y. On the numerator, we have the cube root of x times the cube root of y squared. We can merge those together and just say this is the cube root of xy squared. That's totally fine to do that. And then in the denominator, we have the y squared, and then the cube root of y cubed is just y. So simplifying that all the way down, we would have the cube root of xy squared over y to the third power. That would be the final answer in simplified radical form. So it takes a lot of steps, and you might remember like the rules from Algebra 1 and kind of skip some steps here and there, but I thought it would be helpful to go through the whole entire thing so you can really see it. Part E, we've got the fourth root of x to the 8th, y to the 11th over z to the 6th. So now we're dealing with the fourth root. So what we want to do is we want to try and simplify this as much as possible, because if we look at all of the exponents, 8, 11, 6, every single one of them is all greater than 4. So I know this can be simplified. I'm going to regroup everything into groups of 4 after I rewrite it as the fourth root of x to the 8th, y to the 11th over the fourth root of z to the 6th. Now I'm going to regroup it. Regrouping the x to the 8th into x to the 4ths, or if you realize that you can just divide these, 8 divided by 4 is x squared, you can kind of skip this step, but I do feel like it's helpful. And then for the y's, we're going to need some more space here. We're going to break up 11 into groups of 4s, y to the 4th, y to the 4th, that's 8, and then y to the 3rd, that makes 11, all over the fourth root of z to the 4th, z squared, that is 6. Okay, everything to the 4th power will be able to be fourth rooted. This, and this will all come outside of the actual fourth root symbol. So I'm going to complete the rest of that work right here. So the fourth root of x to the 4th, this one right here, will just equal x. The fourth root of another x to the 4th will equal another x. The fourth root of y to the 4th equals y. The fourth root of another y to the 4th equals y. But we're still going to have the fourth root of that y to the 3rd left over in the numerator over the fourth root of z to the 4th equals z. And we're still going to have the fourth root of z squared left over. Now we can simplify this a little bit, making it x squared y squared, and then times the fourth root of y to the 3rd over just z times the fourth root of z squared. And I wish that we were done, but we're not. We have to now get rid of the fourth root of z squared in the denominator. So to do that, we have to multiply the numerator and denominator by whatever will allow the fourth root of z squared to completely cancel out. And what would cancel out with it is z to the 4th power. Right now we have z to the 2nd. So I'm going to squeeze this in here, but what we need to do is multiply it by the fourth root of z squared. So this right here says the fourth root of z squared is going to get multiplied by the numerator and the denominator. We're doing that so that we can simplify that denominator. The numerator would be x squared, y squared, times the fourth root of y to the 3rd power and z to the 2nd over z times the fourth root of z squared, and then times another fourth root of z squared would be z to the 4th power, which is perfect because fourth root of z to the 4th power really just equals z. So we're left with z times z in the denominator. And if you're starting to realize, like, okay, I need to start like skipping steps because it's a lot of writing, like if this just equals z, then the denominator is going to end up being z squared. And my numerator would be x squared, y squared, the 4th times the fourth root of y cubed z squared. That would be the final